All right, we're going to go over 11-4, series and sigma notation. So a series is just a summation adding up the terms of a sequence. Sigma notation is this. We have a sigma. This letter, it means the sum of the terms of a sequence. So the sum of the terms of this sequence that starts at 3 and ends at 9. So these aren't the numbers of the sequence, but it starts with the third term, or it starts when k is equal to 3, and it will end when k is equal to 9. So first thing I'm going to do is kind of figure out the terms of my sequence. So my first term, or the beginning of this sequence, is when k is 3. So it's going to be the absolute value of 6 minus 3. 6 minus 3 is 3. Absolute value of 3 is going to be 3. So that's the beginning of my sequence when k is 3. And we're going to go all the way up to when k is 9. All right, so the next term of my sequence is when k is 4. We count up 1 from there. And 6 minus 4 is 2. Absolute value of 2 is 2. We're going to keep going here real quick. So the next term, right, k is now going to take on the value of 5. We're going to go 1 more from there. So 6 minus 5, that's 1. Absolute value of 1 is 1. You can already sort of notice what's happening here, right? It's going 3, 2, 1. Next one's going to be 0, and it's going to keep going until I stop. I stop when k is 9. That's the last term of the sequence that we're going to be adding up, the last term of our series here. Okay, so 6 minus 6, 0. 6 minus 7, they're absolute value bars. It's negative 1, but the absolute value of negative 1 is 1. And then 6 minus 8, absolute value. That's negative 2, but the absolute value makes that positive 2. And then the last one where we're supposed to stop, 6 minus 9, it's negative 3, but the absolute value is 3. So the series is taking up all of these numbers in our sequence and adding them up. So it's going to be 3 plus 2 plus 1 plus 0 plus 1 plus 2 plus 3. This is our series written out in what is called expanded form. So expanded form, wrote it out with the pluses in between them. Okay, next one here we have maybe a little more complicated definition of our series. So what the variable expression is that generates our sequence. We're starting when n is equal to 5, and we're ending where n is equal to 10. So we're going to plug in 5, and then 6, and then 7, and then 8, and then 9, and then 10, and then we'll be done. Okay, so our first term of our sequence is negative 1 to the 5th power over 5 plus 2. So negative 1 to the 5th, since this is an odd power, that's going to be negative 1 over 7. Okay, and then keep going, negative 1. Now we go to 6. Right now, n is going to take on the value of 6. So negative 1 to the 6th over 6 plus 2. So since this is an even power of negative 1, we're going to get positive 1 over 8. And kind of see how this is happening. So it was negative, and then it's positive. And now this next one, since our power is going to be odd again, we're going to end up getting negative 1 on top. And then 7 plus 2 is going to equal 9. So it's going to be negative 1 over 9. So as you do a few terms of this, you should be able to see what the pattern is. It's negative 1 over 7. Then it's positive 1 over 8. Negative 1 over 9. The denominator is increasing by 1 each time, and we're kind of alternating between being a negative and a positive, and a negative, and the next one will be positive. So it's going to be 1 over 10, and then 9, and then 10. So, right, because we're going to stop at 10. So the next one would end up being negative 1 over 11. That's when n was 9. And then positive 1 over 12. That's when n was 10. And then 10 is, right, 10 is where we're supposed to stop. So the way that I would write this write this series out in expanded form, -1/7 plus 1/8 minus 1/9 plus 1/10 minus 1/11 plus 1/12. That is our expanded form. We wrote it out with all of our pluses and minuses. So instead of making the term negative, I just went ahead and wrote minus there. I could also have written as plus, negative, but adding a negative and subtracting are the same thing. Okay, let me go ahead and clear this. We're going to look at a couple problems on the back here. So I'm looking at number 6 on the second page of this. We have this series right here. We don't know what kind of series it is other than just by looking at the numbers and trying to figure out what's happening. And then there's a bunch in there in the middle, and then we're going to end with 205. All right. So looking at these first 3 numbers, we can see it starts at 25. That's where it's beginning. And then we're increasing by 5 each time, right? 25 plus 5 is 30, plus 5 more is 35, plus 5 more, next one will be 40, and so on. So I know this is my first term. In fact, I'll just say that this is n equals 1. That's my very first term. I don't know what term this is. So if I'm trying to write out my sigma notation, I'm going to say that it starts at 1. I could call this 0 if I wanted to. I could call it term 1. I could call it term 6 or whatever. Generally, it's most common to either start with 1 or 0. So that's what I'm going to do. But I don't know where it's going to end. And I'm not quite sure of the rule yet. So since this is a constant addition, this is what's called an arithmetic series. Because we're adding a constant amount, it sort of can be thought of as almost being linear in the pattern. We're increasing by a constant amount every time. I'm going to go ahead and write that formula. It's going to be 5n. That's our rate of change for each term of the series. And then plus, for this, I actually have to go back to find term 0, so like kind of one step before the series begins. So, and that would be 20. So now I know my rule, I know where it's starting. The only thing I don't know is where it's ending. So I have to figure out what number of my sequence, if this is 1 and then 2 and then 3, what number of my sequence would 205 be? I could count up to that, but that'd be pretty tedious. I can also use my rule to sort of solve for it, and that's what I'm going to do in this case. So I'm going to take my rule here, 5n plus 20, figure out what n value, what number of my series is going to give me 205. Now I just solve this equation. Subtract 20 from both sides. Equals 185. And then I will divide by 5 to get 37. So we're ending with the 37th term of my series. Okay, so this right here, I didn't go over this too much, but this is one way for us to write the series. If we're starting with term 1, I can write this as my common difference times n. So in this case, my common difference is how much I'm increasing by. If I was decreasing, it'd be negative. Plus term 0 of the sequence. So I have to, if I call this term 1, I would say, all right, what would happen right before that if I kind of follow my term backwards and call this term 0? This is one way to do it. We can do it in another way. But for this case, this is the way that I'm going to write the equation. I could define this differently if I chose to instead start with 0. If I started with n equals 0, that would change things just a little bit. All right, and the next one I'm going to do is number 10. So number 10 is a little trickier. We've got 2/3 plus 4/9 plus 8/27 plus 256, 65, 61, 6,561. That's where it ends. All right. So again, for simplicity's sake, I'm going to call this one number 1, my first term of my sequence. That'd be 2, and this would be 3, this would be 4. It's not so obvious what's going on. It's hard to tell if I'm adding the same amount here or not. It doesn't look like I am. My numbers are getting huge. I need to notice some pattern. I'm going to isolate the numerator and denominator and just think about those. 2, 4, 8. Okay, so I'm going up by 2, and I'm going up by 4. That doesn't really work. But 2 times 2 is 4. 4 times 2. So if I just look at the top, I could think of it as multiplication by 2. And at some point, I would reach 256, because that is a power of 2. What about the denominator? If I think about it the same way, 3, 9, 27. I could think I'm increasing by 6. That doesn't work anymore, though. What about multiplication? And yeah, multiplication works here, right? I'm multiplying by 3. 3 times 3 is 9. 9 times 3 is 27. So overall, what's happening here is I am multiplying. To generate the next term of my series, I'm multiplying the previous term times 2/3. Times 2 on the top, times 3 on the bottom. So we tend to call this the common ratio, or R. If I were to take 2 consecutive terms in my series here and divide them, so if I were to do 4/9 divided by 2/3, I would end up with 2/3. The same way as if I did 8/27 divided by the consecutive term, the one that went right before it, 4/9, I'd get the same ratio. So we call that a common ratio. So now we are going to be, and what we call, when we have a series that has, or a sequence that has a common ratio, that's called a geometric series or a geometric sequence. Or multiplying to establish a pattern. That's different than the last one where we were adding or subtracting. To write a equation in geometric form, let's see here. We'll say we're starting at 1, like we said before. We have to, so I'm going to write the equation or the formula for our geometric series. We start off with term 1. What was our first term? Okay, 2/3. That's our first term. That's what we start off with. And I'm multiplying by 2/3. That's my common ratio. And I can put n minus 1. That's going to be my exponent here. So I'm multiplying by this 2/3 some number of times, some exponent number of times, to get to the given term of our series. So if I wanted to multiply just once, multiply the first one times it just once, I could plug in a 1 here, right? That would make this, sorry. If I want to reach the second term, so n equals 2, plug in 2. 2 minus 1 is 1. That would be equivalent to just multiplying by 2/3 one time. That'd get me there. Now this, you can see, since the first term, our term 1 of our series, and our common ratio actually are the same, we could use exponent rules to kind of put these two things together, right? This would have an exponent of 1. I could add these two exponents together, and I could just think of this series in this way, as just 2/3 to the n. Just sort of ignoring that, because when I add 1 and n minus 1, the 1s would cancel out. I'm going to go ahead and just do it this way, just because if our first term were something different than the common ratio, you probably want to write it this way. All right, last step to figure out is, well, what's this last term? What term is this that we're ending at? I don't know yet, so I want to solve for that. So 2/3 to the n is equal to 2, 5, 6 over 6, 5, 6, 1. Now, really, to solve this, what I would need to be doing is using logarithms. But since that's like a little bit trickier, I really know that I can just kind of look at one part of it. I could just say, I don't know, 2 to the n is going to give me 2, 5, 6. And I can just think about powers of 2. That's not too hard. In this case, the one that's going to give me that is n to the 8th. 2 to the 8th power gives me 256. And I can just verify that that works down here. So for this one, we're going to be ending on term 8. And this is our equation. We don't need this part. That was just kind of identifying what's going on. That would be our series notation, our sigma notation for that particular series up there. Again, alternatively, I could have done this one, right? Still ending at 8, same idea. It's a little cleaner equation, so maybe this one is better, but still, either one works.